In this lesson, we're going to take a look at how light behaves when it hits a boundary. And light is a wave, and so it exhibits the wave behavior called refraction. Now, refraction is simply the bending of a wave as it changes media. Now, this is sort of easier to understand if we draw a little diagram. Okay? So imagine I had a wave, and I'm going to draw wave fronts. So they're coming in like this. Okay? And I'm going to put a boundary right here. And over here we can move fast, and over here we can move slow. So these waves come in and they hit that boundary. Now when they hit that boundary, a couple things happen. Okay? Some of that wave will be reflected, and some of that wave will be transmitted. But the wave that gets transmitted is going to change speed. And so this wave is headed this direction, but this end of this wave that hit first, it gets slowed down before the other side of the wave. And so it's not as far ahead as it used to be. And this wave also not as far ahead as it used to be. So this wave also not as far. And so you can see what happens is these waves that come through, instead of heading in the same direction, they've now bent a little bit. And that's where refraction comes from. It comes from this change in speed, which leads us to this idea of index of refraction. Okay? Index of refraction tells us a ratio of speeds. And the fastest a light wave can move is the speed of light. And so the index of refraction is given the symbol n, and it basically tells me the ratio of the speed of light in the material compared to the speed of light in a vacuum. So the speed of light in a vacuum is c, and c equals 3 times 10 to the 8th meters per second. Okay, 300 million meters per second. Now the index of refraction is equal to the speed of light in a vacuum divided by the speed of light in a material. So the index of refraction of a vacuum is 1, because the speed of light divided by the speed of light in a vacuum is c over c, it's equal to 1. But in anything else, v will be less than c, which means n is always greater than or equal to 1. And the bigger the n, the slower the speed of light. Now, what we can do with that is we can use the index of refraction together with Snell's law to figure out angles of refraction, or how fast the speed of light is in some other material. And for that, let's take a look at a light wave that hits a pane of glass. Okay, and so this is glass, and so let's say it's got an index of refraction equal to 1.5, and on either side of the glass is air. And air has an index of refraction almost exactly 1, so we're going to call it 1. You know, we don't care about the 0.00003 or whatever it is. So here is a beam of light. Okay, that's what we call the incident ray. It hits the glass. Now we're going to draw on our normal, just like we have with reflections. This angle right here, I'm going to call that theta 1. That's the angle of incidence. Okay, it's where the incident ray hit the glass. Now, had this not been glass, or if it did not have a different index of refraction, this light ray would have continued in this direction. But because it hit this glass, it slows down and it bends towards the normal because the light ray is getting slower. So I have this angle, theta 2, and theta 2 is related to theta 1 by Snell's law in the index of refraction. So over here, air has n equal 1. Over here we have glass, n equals 1.5. I'm going to call this one n1 and n2. And Snell's law says n1 sine theta 1 equals n2 sine theta 2. And so if I know the indices of refraction and I know the angles, I can, or one of the angles, I can figure out the other angle. Now this light ray will continue through this glass, and when it comes out the other side, okay, there's my next normal. This angle right here is the angle of incidence, because the refracted ray is now incident upon this boundary, and then when it comes out of this, instead of continuing straight like it was moving, it will bend back this way, and this angle between the normal and my now refracted ray is going to be my angle of refraction. Now what's cool about this is this angle right here is the same as this angle right here, because those are alternate interior angles of two parallel lines cut by a transversal, which means this angle, I'm going to call it A, and this angle are also A. So over here I had n1 sine theta 1 equals n2 sine theta 2. Well, now I have, this would be my N1, and this would be my N2, and this would be my theta 1, and this would be my theta 2. You'll notice this is going to be the same equation, it's just the left side became the right side, which means when this ray of light goes through this piece of glass, it enters at the same angle it exits, but it changed path in between. And what that appears to make something do is shift position. So if we're observing up over here, we're going to look at this light and our eye is going to assume it came from right here. And so we see the object that this light is emanating from as though it's right here, when actually it's right here. And so refraction is actually responsible for some optical illusions that happen. Like when you look through water and something looks shorter than it is, or a straw looks bent coming out of your cup, that's because of refraction. Our eye assumes the light bent straight, or went straight, when in fact it actually bent at a surface.